video, we're going to review chapters 12 and 13, starting with some definitions. Suspensions are large particles that will eventually settle, like mud for example. Colloids contain small particles that will scatter light, but that don't settle, for example milk and fog. And finally, solutions contain particles on the size of individual molecules or ions, and as a result of the very small particle size, solutions will be translucent and will never settle, and they have a uniform concentration. Some more definitions. Solutes are whatever are getting dissolved. A solvent is what dissolves a solute. Note that the solvent will always retain its phase in a solution. For example, salt water looks a lot like the solvent water. Solutions may be electrolytes, which are conductive of electricity, examples being any acids or ionic solution. A strong acid will be a strong electrolyte, a weak acid will not produce many ions in solution, and therefore will be a weak electrolyte. Non-electrolytes contain covalent compounds and do not conduct electricity. There are three factors that affect the rate of dissolving, those being temperature, the surface area of the solute, and agitation. Agitation or stirring brings solute in contact with fresh solvent. A crushed solute has more contact with solvent that can dissolve it, and a hot temperature means particles are moving faster, causing solute-solvent interactions to happen at a faster rate. Temperature will also affect the maximum capacity or solubility of a solute in a solvent. Moving on to solubility, there's the principle that like dissolves like, meaning that nonpolar solvents will dissolve nonpolar solutes, and polar solvents will dissolve polar solutes and ionic solutes. The exception being that if there's a very highly charged ionic compound, it might not be soluble in water. Generally, solids become more soluble at higher temperatures, whereas gases become less soluble, and gases become more soluble at higher pressure, according to Henry's law, whereas pressure will not affect the solubility of solids and liquids. A system is unsaturated if it's still possible to dissolve more solute in the solvent. Once we reach that maximum capacity, the system has become saturated, although a supersaturated state is possible if a saturated solution cools, thus decreasing the solubility of the solute. That is an unstable situation in which crystals will likely grow if the system is disturbed. Next, we have enthalpy of solution. When something dissolves, it may release heat or absorb heat. Every dissolution process involves two endothermic and one exothermic process, and the magnitude of each of these processes will determine whether the overall dissolution process is endo or exothermic. The solvent particles and solute particles must separate in an endothermic process, but when the two come together and form IMFs, the formation of attractive forces is an exothermic process. Next, we have concentration of solutions, which is loosely defined as the amount of solute per solvent or solution. The most common concentration that we use is molarity, which is equal to moles over liters and has those units. In solution stoichiometry, we should use molarity for any conversions between moles and volume. Moving on to precipitation reactions. Just because you mix two solutions together does not necessarily mean that there will be a reaction that occurs. You always need to check the potential products of a double replacement reaction, and if there is an insoluble compound that results, then a reaction occurs. You should refer to the solubility rules in making that determination. The term spectator ions applies to any ions that don't change during the reaction. They start off aqueous and they end up aqueous. And finally, we have an example of a reaction between an aqueous solution of lead-2 nitrate and an aqueous solution of potassium iodide, forming a precipitate of lead-2 iodide, while the potassium and the nitrate ions turn out to be spectators. If you understand the molecular, full ionic, and net ionic equations, as well as the pictorial diagram here, then you know what you need to know about net ionic equations with precipitation reactions. If not, I encourage you to go back to the video on net ionic equations and double replacement reactions. But that's all for this review video. I hope it's been helpful. Feel free to leave any questions or comments in the comment section below, and thanks